You're a program and 200 people working.
Too expensive.
Yeah.
Too expensive.
Yeah. We can spend 1 billion.
Oh, are you a teacher or something? That's what I tell my students. And then I must keep with answers. But no questions and reason. As we tell the students.
Back into the firing line.
So.
Geez, minimal effort. Minimal effort. So you were up early tonight? Yeah, I always see that whenever I turn on my computer. I also wake up much too early here, but I always see Steve is already on Skype.
I can't help it. I wake up early.
Me too, no.
It drives me crazy. I hate it.
It's terrible. I'm totally wiped out. I need a 4 weeks vacation when I come home. So these meetings here.
Okay, let's get started. The sooner we start, the sooner we finish, and we have to remind ourselves that being late for lunch is a sin, and we should be without sin. So we've gone through the first 2 questions. There are 2 remaining, and we'll start this session with the 3rd question, which is, what is the most relevant way for theoretical work to be shared with generator authors? And why don't we start with Steve?
Okay.
And there's slides if you need them.
Yeah, now I want my slides.
Okay.
Are they?
They're not all together, they're in separate files. Okay.
Let's see. So Hugh has some slides also, and I'd say very much what he's going to say and what I'm going to say are complementary. So, so I thought he would go first. So.
Oh, we can arrange that if that's easier. Is that?
Whatever.
I think we could do it. I think we could do it either way, yeah, really. Right. Here's how I view building models, because I've been doing it for a number of years now, and this is my philosophy. If people don't agree with my philosophy, maybe now's a good time to hear about it. We have. Okay, so would be nice if we had a single process that started with everything. We started working with Steve Moren at Fermilab, and he says, "Gee, at Pythia, there's we have an ASCII interface. It's 20 numbers, and any theorist can interface to what we're doing." Nope, we don't have it. We have a principal vertex of many types, and there are unfortunately different physics. So. That's complicated. We get one piece from one person, another piece from another person, and then we try and fit them together in some way. We do try hard to do that. Then they are embedded within a nuclear model. Someone can just provide a nuclear model, and then they have hadronization and final state interaction. So it's a necessity, sort of a fairly complicated mixture of things. And I think it's largely due to the fact that we have nuclear targets. And doing that all consistently is hard, but each of those red things is something that someone could contribute to. And I talk to many theorists, and I apologize to anyone I haven't talked to, because each time I talk to a theorist, I try to figure out what they can give us and try to figure out the proper interface. And it's always in one of those. And yes, it's hard to generalize, especially with 2-body currents. Comparing to data. That's okay. That's not. I could talk about that later. That's 5 minutes.
Okay. Is it?
Yeah. So this.
So I should say my starting point for this too was also, I guess, some conversation. Well, number one, the work that people are already doing, and number two, some conversations that we had again with Collider people at Pitt in May, because when we started, he started hearing about these double counting issues and all the inconsistency. He said, well, in Collider physics, we don't have that problem. Theorist A does this calculation, and theorist B does that one, and theorist C does that one. And they know in advance that they're not supposed to overlap with other people what they're doing. And it'd be great if we had, the 5 different ways that we think about things. Theorist A did one, theorist B did another, and then we just added them all together at the end. That's the wrong physics, and we know that pretty clearly. But that's, often the way that we, historically at least, have tried to, plug things together into generators. So one of the things that I was reflecting on is that, we heard it a lot of times at the meeting. Already Jerry had it in his talk. The work in incorporating the Nieves model into Newt is basically doing this already. And I just wanted to, make sure that I understood, or that on the generator side we understood what the technical pieces were. This is maybe a little bit too technical for a long discussion, but it's clear that the theorists are going to calculate what they're going to calculate. They have a model, they have a set of things that they're interested in, and their calculation is going to be what it's going to be. And we need to think about, I think before we get too far, at least in my mind, into the conversation about how to avoid all the double counting, and boy, it would have been better if you hadn't included those diagrams in what you did, because then maybe it'd be easier to patch together with something else. Before we can do that, I would like to have the pieces. I would like to have the ability in a generator to take the best theoretical calculation that somebody can do and at least have it available to us. Then we can have the conversation about how does this fit into a more overall sort of model. So this was, that was just the general, part of the idea. And I think the thing that we, again, coming out of the generator workshop at Pitt, was the idea that, we don't want to have to link people's code together if we don't really have to. And so the idea of having theorists calculate for whatever process they're most comfortable calculating, inclusive processes in particular, what we need to plug it directly into a cross-section calculation for at least the inclusive distribution. So I think from the work that we heard from Jackie and Esmita, they had a way that they were doing that in Newt, and in talking a little bit more with Federico, it seems like if you just give us the components of the hadronic tensor, we can calculate inclusive cross-section. Okay? That at least guarantees, number one, that when we produce the left-hand distributions from our Monte Carlo, they're going to look exactly like the left-hand distributions that are in your papers. Okay, that's number one. It's a simple thing to do in the code. That information could go into all the generators in the same way. And then Tepe was asking, well, maybe new ECC is different from new UCC. I mean, we get that all automatically. At least that part of it. So again, this is I think this was the kind of thing, Jerry, that you were also pushing for. But I wanted to, number one, make sure that I had that idea right. That there's sort of a consensus, or at least maybe not a consensus, but if that's really what we want the theorists to be giving us, if that makes sense for them to be giving us, and if so, I wanted to kind of spell out what I thought we really needed. I think, again, this is a nuclear theory workshop, and we heard nuclear theory calculations. I would love to have those for the neutrino nucleus, not neutrino nucleon. And I think that's what most people are calculating. We wanted them separately for the weak charge current, weak neutral current electromagnetic processes, so that we can do electron scattering comparisons as well as the neutrino stuff. For the reasons we heard before, for as many nuclei as you're able to calculate, or if you have ideas about how to take what you have calculated and maybe modify them for other nuclei, that's fine. And getting back to something that we heard yesterday, if they can, tell us something about the uncertainty on the model and some uncertainty on the calculations. And so that's, so that maybe that's the most important thing. And I'd love to hear from, Jackie or Federico and Esmita. I mean, you're the people who've done, at the cutting edge of trying to do this in the generators, if that sort of worked. For you, if that set of things is not actually what you needed or wanted, or what you think we need, or there's more to it, or from the theorist, if that isn't the right kinds of things for you to be calculating, if there's a different way to be trying to plug these pieces together. But it seems that that's one way to at least get the best and very detailed microscopic calculations, at least part of it, into generators pretty quickly.
And hadron final states.
Yeah, so that's the next part. So
We have two other.
yeah, Yeah, so then we know we got to take that part of it on. And what I wanted to reiterate from the discussions is, we know you can't do a calculation, but we're going to make something up. So, just give us your best guess. So just continue to talk with us, and we'll do something, and you can at least tell us if it's totally stupid. And then, we'll down the road need to think about how that does or doesn't overlap, what we're doing wrong with regards to other processes that we might be trying to also integrate into the generator, and just continue to communicate with us, I guess, about how we're doing that and the problems that we're hitting there. Yeah.
I would add to this, just echoes Mosel's point, that I think actually one of the best ways to communicate about how to generate the hadronic system is to write down clearly what the generator is using for the hadronic system,
Yep.
and then have them pick it apart.
Yep.
But I think it'll make it really clear what assumptions go into it
Yep.
and what might be blocked.
Yep. Okay, and then I guess the last slide was, again, this gets a lot harder, but it comes back to the point Scott was making in his talk yesterday, really trying to help clarify how we use these models in our experiments. And I make an even stronger statement, perhaps, than what Scott had expressed, which is in some ways when we're doing these fits, but in particular near detector, far detector fits, we care more about the uncertainties on the model than sometimes we do about the model itself. We need we need to really understand what the wiggle room in the model is, because the goal is really to be able to fit the data and do an extrapolation to do the oscillation physics. So when I hear from a theorist that, I can't, the uncertainties aren't so important, we just do the very best we can, and then we see our job is done. If that's the attitude, we will always have a problem. Okay, and so these were just some ideas about things that we've tried in the past when we dialogue with theorists about uncertainties. And sometimes they're very generic statements, like, well, I think that term is probably, we probably know it to 10%. I mean, even that, it's not a detailed fit or anything like that, but even to have generic statements like that are helpful. Then there were just some other ideas. If there are places in the calculation where you had to make a guess, or you had to make some kind of choice, well, you could give us both choices, right? We could take the difference in those calculations as an estimate of the uncertainty.
I would actually say, well, it's somewhat useful to have, well, I think we know that to 10%, knowing that there's not actually a quantitative estimate of the uncertainty on a particular parameter is useful, because I think then we need to figure out how to get one.
Yeah.
I mean, I think it's somewhat helpful to have that as a starting point for fits to data, but I think especially going forward for neutrino oscillation experiments, where we're going to, in principle, stand before the world and say we either have or have not discovered leptonic CP violation, I think we need to be, the level of rigor has to be stepped up. And it doesn't mean, I mean, I think it's not there now, and it may be impossible to be there now, but we should at least know where there's an issue. And so if there's some parameter and there really is not a good quantitative estimate of uncertainty, we should know what that is, we should know what the issues are, and then as a community we should try and figure out how to either measure that quantity, or extract it from data that have already been taken, or get some quantitative measure of the uncertainty. I think that's really crucial. But identifying those things, I think, as you pointed out, is very important.
Yeah, and I think the last couple points here just sort of get at part of this. I mean, the historical way we've often done it is by just having different models available that have taken different approaches, and then the difference between them gives us sort of a direct way of getting at some of these things. And I've often noticed that sometimes it's not just true theorists, but generator developers or anybody, we're better at identifying the problems with somebody else's approach than seeing the problems in our own approach. So to have conversations like that are also helpful, because it's very hard for us, or just for myself, I would say, in some of the exchanges between the theorists, I heard about a very nice model, and I thought it was the best model I'd ever seen, and then somebody said, well, that doesn't conserve current. I think, well, that sounds terrible. I'd have to put a 300% error bar on that if it doesn't, but that's obviously not right. So I need the theorists to tell me how bad some certain approximations or limitations are in models, because often we just have no idea.
Let me ask the following question,
Yeah.
just to understand
Yeah.
what you would need. Suppose we were to sort of provide you with sets, the differential cross the inclusive cross section depends on the defined response function.
Yeah.
So suppose we were to give you tabulations of those response functions,
Yeah.
Up to say pre-momentum transfer of 500–600 MeV, and omega, covering the physiologic peak region, maybe up to 200–300 MeV. Would you be able to stuff from the tabulations and implement into your generators. And that would be a treatment of the quasi-elastic sort of thing.
Yeah.
Of course, yeah, of course,
Yeah.
of course.
You,
Yeah.
you could do that.
Yeah.
So if we provide you with tables, maybe you would have to spline it or interpolate.
Yeah.
Q and omega, you would be able to use those.
Yeah.
That's the closest we can come
Yeah, I
to what you need.
yeah, and as I understand it, that's basically what people in Newt are doing right now with the approach in the Nieves model. Although I guess you have tables for the doubly differential cross section and not the response functions, but I guess the response functions are really the right place to start. So
this
yeah, I
is
would
a-
say absolutely. I mean,
Yeah, this is
But
a format which,
maybe it's not
which
all.
one Nieves
Maybe
is
it's not
providing.
all one needs. What one needs. I mean, this is inclusive information.
Yeah,
Yeah.
How to make the correct link, so to say, to the more exclusive things. That's the.
But
Yeah,
this is
I
this
guess-
is a starting
I
point.
I guess what I'm saying is that we talk a lot about that next step, and in the generators, we haven't always gotten the first step. I would love to have just have the best you got, right? And that's the best you got, then let's plug it in, let's see at least the left-hand side we can, we're happy with. Then it makes it easier to compare to the same kind of calculation other people might be doing, and then it allows us to take the next step, so yeah, absolutely, I think that's what we need. Again, as I said, for all three currents, if you can.
Yeah.
And the other thing, I think when I talked with some of the theorists, they're saying, well, that would, to have it at the level of resolution you need or over the kinematic space, that would be more, computing resources than we have. I mean, we could always find computing resources. If any of these theoretical things are CPU limited, I'm sure that's something we could solve together.
We're more manpower limited than CPU.
People seem to be happy to give us CPUs. They don't want to give us
You are
PPUs.
not
My-
limited.
Why don't we let Jan?
Yeah, just for a second, because I mean my kind of obvious worry right now is, because you are saying that you can calculate these tables up to say 600 MeV over C for momentum transfer. So for for experimental community, it means that it covers a region in Q squared. This is a value that experimenters like. At most 0.36. Okay.
Yeah.
So it means that there is there is a big piece of the phase space which will not be covered. So
Right.
But
It's
But
like
so-
when you compare it to,
so
yeah.
we will have so there there will be many problems to solve. To combine, to put together.
But
Yeah, but at least you can compare.
Yeah,
So
okay,
you
yeah,
understand
I know,
what's going on
it is-
with
it
all
is-
the models there where it works, and it will give you an idea of what you might be missing.
Yeah. So and it's just a comment that it is not that we will know everything.
No, no,
course
no,
not.
yeah.
Of course not.
Yeah.
We certainly don't have any real time and action mechanism for the theory, so it's really limited to the quasi-elastic region. But within that
In the
limitation
region
is
is-
the
yeah,
best
yeah, yeah.
one can do
Okay.
in
Will
first
be great.
principle calculation.
So maybe, Hugh, I'm not familiar with these, the Lesusha chords or whatever it was.
Yeah.
But, certainly one of the places where one can see a challenge, and I'm not sure if the Collider people had to confront a similar type of challenge, is, there's clearly a big difference in terms of, for example, if you just look at inclusive versus exclusive channels. And so, I guess in general, the generators are going to need to be able to accommodate both in a somewhat independent way, so that maybe you get some inclusive channels, and then from a practical standpoint, an experiment may have to go through and say, well, look, maybe we know the inclusive cross-section very well, and maybe the relative strengths of the exclusive channels are not known very well, but are going to have to go through and do some kind of fitting, but with a constraint from the inclusive. And that, I'm not sure if colliders have had to deal with that kind of polypath approach to doing physics, and so that may be, it certainly raises its head as well.
Thomas.
My turn?
Yes.
I wanted to make a comment about this discussion on using the results of very sophisticated non-relativistic calculations. And it is certainly true that this is the best you can do in terms of nuclear dynamics. Because, and in principle, yes, it would be very useful to say, well, okay, I know what to do up to 500 MeV momentum transfer, so why don't I use this stuff so that I can get a handle on this part of the phase space. But unfortunately, in neutrino physics, this is not trivial, because I mean, if you pick any bin in muon energy, say, I mean, you're mixing up different momentum transfers.
Correct.
So this separation of non-relativistic versus relativistic is very elusive in neutrino scattering. So what one should try to develop is a model that incorporates as much as you can of what we know of nuclear dynamics into a relativistically consistent framework. And well, I mean, my religion is that to do that you have to factorize the vertex, but that is up to the open for discussion. But the point that you don't really know the momentum transfer is a fact.
Right. But I think I think because I agree with you, Omar, I do think we need the ability to do some things like this, because as you say, in our experiments, we wash over a lot of kinematic space in any one bin of a reconstructed quantity. But the only way I know to get a handle on that is to at least at the the truth level have a better model for the part of phase space where people think that model is better. If it turns out that I have that running in the restricted phase space where it's supposed to work, and it doesn't make a difference at all to that particular observable, then I know I don't really care. And I know that even though I haven't combined things in a way that's theoretically consistent, I'm not sensitive to it in my experiment. I mean, we might find that, then that could turn out to be true, and that would be great news for us in some sense. It tells me we don't need to worry so much about the theoretical details of tackling some problem. It makes clear what observables are sensitive to the detailed nuclear theory calculation and nuclear theory calculations, and which ones aren't. Because as you said, I agree with what you said, but I don't know that we always are able to say a priori, what observables are going to be the most important in some of these discussions.
Well,
so
we'll be
maybe,
talking about the response. So what I had in mind was obviously a double differential cross-section.
Okay.
The double differential cross-section, we know for a fact that if you pick a single bin in muon energy, you are collecting strengths for different momentum transfer. So that's it.
So this discussion is concentrated basically for the generators, but even if we have those kind of distribution, whatever the limited, but we can always compare with the generator what we have already, and then if we can compare and see some differences, then we can assign systematic uncertainty on that, and that will be really useful for the actual experiment, whatever you can provide. So the easier way for us to compare with the double differential function maybe, but if you can provide a proper way, then we can use that for the getting out of the physics results from our experiment. So it will be really useful not only for the generator but for the physics analysis themselves. So it's really fruitful.
It's also useful in a final sense of just making comparisons easier. So if we have sort of a standard format where you're handing things from different theorists, the theorist, now you have somebody who can make an automated script who can do these comparison plots, and maybe the work can be centralized instead of tiny comparisons going on everywhere. So I would say as a final thing, and for validation and also cross-understanding other people's work, this is also a useful way to centralize that.
I'm sorry, but I understand where Omar's coming from. This is really good. Don't get me wrong. I'm ecstatic if this can happen, but it's not the end. It's a good way of getting an overall picture of things, and you still have to have the components of the model. It doesn't tell me what to change inside of the model if there's a 30% difference. So
I'm just saying it's barely the beginning, but it seems to me that it's a relatively simple technical issue that would at least get us a little bit further down the road.
yeah, that's what I meant.
And once we start some comparison, then we can feedback to the service, and we have seen these kind of differences. Then the people can comment, ask the people what might be wrong with our side. So that will be also important for us because we can modify our code or whatever the model is much better.
If you understand the underlying physics.
So in short distance, I mean, there is an issue of because until we get those better results for limited part of the phase space, but still would be great. I mean, we must live with remaining, I mean, with models that are at our disposal. Yeah, I would be interesting to, I mean, to know the opinion of experts, which is the most, the best combinations of models. I mean, to keep, also to keep some consistency. I mean, this is, I think it is important after all. And so for example, currently in Newt, there's Fermi gas. I mean, there are works going on RPA, correction on top of it. Is it local Fermi gas or global one? I don't remember. For quasi-elastic.
Well, I think it used to be the global.
The global Fermi gas. Okay, so and on the top of that, there are works on implementing Nieves model for two-body current. So my feeling is that I mean, for that in the quasi-elastic, I mean, feeling also, I mean, experience that in the quasi-elastic peak region, spectral function is doing the job better than Fermi gas, also with even local Fermi gas. So I would prefer to use Omar's spectral function instead of Fermi gas. But there's an issue of which I mentioned that yesterday. So I'm worried a little bit about consistency, because in the spectral function there is an inherent contribution from leading to nucleon knockout. Okay, I mean there is a contribution from correlated pairs, and so there is some double counting. Potential double counting, because if you combine spectral function with,
it depends. If you're
okay,
talking about,
okay, so
if
okay,
you're talking about,
yeah.
I don't know, Mark can correct if I am wrong. In the spectral function, you may have a particle spectral function and whole spectral function. If you take into account whole spectral function, then you don't have any double counting with the two-particle two-whole mechanism that we are. If you include particle spectral functions, then you may have some double counting in principle. Though I must say that in our model, this part has been eliminated. The one that corresponds to particle spectral functions.
Look, two final states can be introduced through three different mechanisms. Initial state correlation, final state correlation, and two-body current. Okay? Now, if you do things right, I mean, all you have to do is just to compute the matrix elements of the one-body current, the two-body current with realistic initial and final states, and then do quantum mechanics properly, so take into account interference. And that's it, and there is no double counting. If you sum the cross-section, that is a problem, because it's not quantum mechanics.
Well,
It's as simple as that.
I think that we will have time to discuss about this, but I mean, this in
Anytime.
our model respect, we do a proper quantum mechanic calculation, and then we will take into account interference between two particles.
Yeah, because
Because
you include a term in the two-body current which is not actually a two-body process. You put initial state correlation in the two-body current.
I don't know initial state.
Otherwise, we won't have interference.
I don't read. I mean,
Okay,
this is
so I don't think that
okay.
people are really interested.
Okay. Okay.
Okay, now you see the.
Sounds like an interesting discussion.
No, because in the
No, but
as far
tomorrow I think that we'll have time.
yeah, as far as I understand, in the inclusive computations, I mean there is a big interference between one body and two body. So
Currents.
currents, yeah. So I think it is a source of work.
Yeah.
Loco, could you comment?
It's exact. I think it's
That's
the
what
same
I'm saying.
mechanism that it was Omar was
That's what I'm
mentioning.
saying.
If you have a correlated, if you start from a correlated state, even if you have a one-body current, you can put two-party would be, you can't create a two-party
Sure.
with one amplitude
Sure,
in the
sure.
presence of correlation.
Sure,
And
sure.
so, and that
I don't disagree with that, I don't disagree
Yeah,
with that.
so I mean,
I don't disagree with
think
that.
that's.
Yeah, but in this way, I mean, we add, we combine models on the level of cross-section, not amplitudes. I mean, because we add the cross-section from spectral function and cross-section
No,
from.
but that's
So
that's
is
the
that-
problem,
No, but
right?
they-
I mean,
Yeah.
because what you want to add is the amplitude.
Yeah, okay. So this is what,
and
this is what I'm saying.
That is the
But
problem.
then I come back
We
to
don't
my
have
point.
amplitudes, and it's hard to have amplitudes.
So which
I
is,
understand.
so,
But
that's
then,
why I told you that what we can, the best we can do from our point of view is to provide you with a response function which are properly taking into account this interference between one and two modes. It's all in there.
Yeah.
We have correlated initial and correlated final states, dynamics, it's all set. But that's, then you just take those response functions and you calculate the cross sections that you need to simulate whatever you need to simulate, and then
Okay.
that's it. I mean, you don't have to then,
yeah.
you don't have any model, you don't have any
No, no, no.
parameter that you have to choose. That part, of course, it's limited to the
Okay.
to the region to the kinematic region I was discussing before, but you don't have to do that's what nuclear theory gives you.
yeah.
That's good, but then we have to use sausage, to use the term we generate, we were talking about last week. We have to make sausage
Yeah.
to actually give your beautiful result.
What is sausage?
We have to put pieces together that may not have the physics that any theorist would want, and we do operate on the cross-section level. We have a separate one-body piece and two-body cross-section piece, and we
Yeah.
generate them independently.
Yeah, okay.
And then that's clearly a problem. Clearly,
That's the
very clearly.
sausage.
So,
Yeah.
And on the sausage market, of course, there is also some sort of quality control around, okay? Because not every sausage is good for digestion, you know?
I understood. Okay, so let me ask again. I mean, can we reach a kind of consensus? I mean, how to proceed before we get this coverage of the piece of phase space in the most proper way, and which is the best way to proceed in Monte Carlos we have.
I think it's hard to get consensus here.
Okay,
But
yeah.
I think that's why NewsTech
Not here, then where?
the NewsTech, this regular meeting.
Right, we're gonna talk about how to actually continue these interesting discussions on a regular basis this evening,
Here.
Yeah, let's, Jerry,
So just try to understand some vocabulary for experimentalists. Spectral functions are one thing, and they are presumably interesting and valuable, but I would have thought that what one really wanted were response functions.
Well, you can, I mean, the response function is, how do you construct a response function? I mean, some of the relevant matrix element of the current, the
Yes.
interaction current, okay? Now what the path to go from the full response to the spectral function is that you say, okay, at large momentum transfer I can write the final state in a factorized form. And that does the trick, because then you're left with the spectral function times the matrix element of the current. That's the trick in the sense that the spectral function you can legitimately compute with the non-relativistic theory, because this is an initial state problem. And then the matrix element of the current you can use the fully relativistic expression, because this is kinematics. Relativity is kinematics there, as long as you can neglect final state interactions. Okay? Now, the point that I made in the paper that just came out last week, and that maybe if I have a chance, I may try to make here too in the coming days, is that you may, and this approach has been successfully reproducing the responses. I mean, the spectral function is a framework to write the response at large momentum transfer. Okay? Now, the question is, can we devise something similar to write the contribution of the nuclear current to the response? My suggestion is that, yes, it's not trivial, but it can be done in the sense that in exactly the same way as you factorize the final state as a minus 1 non-relativistic system times the ejected nucleon, you can factorize it in terms of A minus 2 interacting non-relativistic nucleons times the nucleon pair. That is what goes into the matrix element of the two-body gravity. This involves further approximation, because besides the final state interaction between the ejected nucleon and the spectators, we have the final state interaction between the two nucleons entering the matrix element of the body garden that you are neglecting. But that can be, I mean, there are, I don't want to make it too long. I mean, the idea is that you extend
How do
this.
you deal with that?
Well, the two-nucleon scatter factor has been computed actually about, for infinite matter is there. I mean, it's been computed about 10 years ago and it's published.
Yes?
So,
But can I make a question on that? Could you describe
can I finish?
Sorry, excuse me.
So, I mean, this can be implemented. I mean, it takes time because it's more complex. I mean, the kinematics is more complex, but I mean, the conceptual framework is there. This is my claim.
Can I make the question now?
Yes.
Could you describe the deep region, the region between the quasi-elastic peak and the delta peak using what you call a spectral function? Because the key point is that these two particles, and Marco is here around, right? The key point is that what we are calling two particle, two Hall mechanisms, there are some of them which are the less relevant, which can be, its origin can be traced back to some initial state, never initial state, but final state interactions, particle spectral functions, or eventually there will be also some Hall spectral functions. But the bulk of the contributions comes from those mechanisms that describe the deep region in the electron scatter.
That goes in the magic element of the current. This is exactly the same thing that you do. I mean, what you do.
But then you have to present both things. A proper current and then.
Absolutely. And I said that, I mean, the trick of factorizing the final state is needed to use the fully relativistic current. I mean that's exactly the idea. What I'm saying, what I'm worried about concerning your calculation is that this matrix element of the two-nucleon current is just fine. There's all kinds of meson exchange, but then these mesons disappear in the description of the initial and final state. Can I call this inconsistent?
This meson disappears.
Yeah. Oh, they go into new field.
No.
So this sounds like.
I suggest that these two persons have lunch together.
If you family lunch, it's okay, right?
No, I skip lunch as a rule. Everybody knows. I mean, I'm not just making this up.
I will buy the lunch.
Okay, why don't we?
So can I join?
I think we should. Do we have any final comments on this topic from our panelists?
So you still want to get to another topic?
I'd
Is
like
that
to
right?
get to
Yeah.
that last
Can I
question.
add something?
Because I have the last word on the last topic.
Can I add something? There
You get the first word.
there is
I
a
get the
magic
last
word that I haven't heard.
Then you
It's
can digest it
RPA.
over lunch.
That happens with RPA, right? I mean, because I think RPA effects are, and these are low energies and low momentum transfer, are well established. I think that all the theories will agree on that. And I think it will be very important. I mean, because Jan was saying that the best model will be used to use a spectral function. I agree, because I mean, spectral functions are only to include the dynamics of the nucleus instead of a nuclear medium. But on top of that, I mean, the dispersion properties of the nucleon changes, but on top of that you have RPA corrections, right? So the best model, in my opinion, will be to have a whole spectral function, or a spectral function, if you want to call it a spectral function, but then you have to add on top of that RPA effects. And you cannot ignore RPA effects just because you don't understand. Because then what I propose to you is try to describe muon capture. The data muon capture without including RPA effects. I think that it's very important to include RPA correlations to describe the low energy, the low energy part of the spectrum. I mean, for low energy transfers and for low momentum transfer, one needs to include RPA.
Yeah, that I would agree. There is
Okay, so
something-
it's a starting point.
But this can be done in a very consistent fashion. I mean, with the spectral function format. I mean, RPA, if you wish, is a property of the final state, right? I mean, you write the final state as the forward position of particle.
I'd like to come back to more
I mean,
generator
yes,
discussions.
let me put it to the extreme. I mean,
This
RPA is a way of
we
modeling
had a whole week on
particle
QE, these
spectral
guys,
function.
but yeah, no, they start their own
Okay,
project.
let's, I think,
Well,
no,
but I mean,
you
you
can-
Can we talk about generators,
Trouble is,
please?
I mean, last week,
That's a great idea.
okay, so, any last comments on this third question, or is it time to move to the fourth? Okay. All right, so the fourth question, was really, there were a few suggestions for exactly how this is worded. The basic idea is what is expected from a generator, and I think a slightly more focused idea is where do we want generators to be 2 years from now? That is what features need to be there, and need to be, if they're not already there, need to be implemented in the next 2 years. So we can start with Steve, if that's a reasonable thing, or I don't know how you and Steve want to.
Or Steve has the first word and I get the last word.
That's
I don't
okay?
have it,
Yeah,
yeah,
that's
so
fine. Do you have slides?
No, okay, all right.
Sure.
I mean, this is a subject I've been thinking about quite a bit, so my philosophy sort of starts with the building model slide that I had. I mean, I try to think about how we can advance each of those elements. There were at least 5 elements.
Do we want to bring them up?
I think everyone knows them. Well, it's the principal vertex, it's the nuclear model, it's the final state interactions, and the hadronization. And there are multiple principal vertices. So
Is this it?
each theorist has something to add to this, and we need to find the right way of interfacing with them. So there are a number of activities already underway. I could list them, but I don't think that's appropriate. And we're always interested in finding new theorists to work with. And what's become really, really interesting is trying to find the right way of interfacing their information. And the right interface with you guys has become the total inclusive. That's fine. For other people, it's different. And I don't want to be rigid about it. I want to figure out the right way of doing it. Like I had really interesting conversation with Joe Carlson, because that is one of the most complicated ones. And each time we talk, it gets more and more complicated and or interesting, but it's starting to appear solvable. And I think that's enough.
So what was the essence of that conversation? So I didn't hear you guys there.
Well, he says it's very complicated because I have a full nuclear current. I mean, I have everything going on, and but I have to see how's the interface to the way we do things. And we say, well, what's the 1 nucleon component? What's the 2 nucleon component? Which is an artificial separation. And if the conclusion is that is impossible, then we're going to have to think really hard what to do. Because we cannot have a full nuclear model in there, I don't think, unless we have enormous computing resources. So what I suggested, and he wasn't that happy with it, but I said, well, what if we had the full 1 nucleon distribution with all the quantum numbers, and the 2 nucleon distribution with all the quantum numbers and velocities? And then I could see us starting to build on that, and I could tell he didn't like it. But he was willing to think about it. But so I see that it's still evolving, and I really want to have what other people think about it also.
I mean, you really want slices of the sort of exclusive slices of the inclusive process.
Yeah.
That's what you really want, in a way. And that's going to be very hard to sell. So
Yeah, he didn't even want to talk about that.
I don't think that's going to be very. I mean, it's going to be hard.
That was sort of the consensus last week, is that that it's so much to ask of you guys that we shouldn't ask for that.
If we had been able to do that, we would have looked at the E prime P processes within the same framework, which we haven't done. Precisely because that's a little considerably more complicated.
Yeah, yeah.
There are tons of E prime P experiments
Yeah,
could have looked at, but we haven't, because for us now, if you start looking at exclusive, then that's considerably harder.
Fine. I mean, Bill was saying exactly the same words last week. So.
Exactly. Bill said it went from something like 5 responses to something like 16.
Yeah, of course. I mean, that's yeah. But yeah, it's going to be much harder. I think what is conceivably that we could do is certainly, presumably within the same methods, we could calculate spectral functions. But I think the approximation that people are already using, sort of, they're not going to be that different from what you already had, I suspect. I don't know that, but I suspect it's not going to be very different. But the
Still,
idea
it
that
would be great to have a spectral function calculation with this function integral.
yeah, that could be done. I think that's feasible.
I know it could be done, but you don't want to do it.
No, but now there's some young, there's some
Yeah.
young blood.
Yes.
I just want to be clear, really, where the spirit of some of the things I was saying were coming from, because I feel like we're coming to these kind of conferences now for a lot of years, and trying to tell theorists what it is we need, and they just can't calculate what we need. And I finally have accepted that fact, and I'm saying I'll just put in whatever you got. Give me your best. Give me your best at whatever it is you have the tools to do, and let's see what we can do, make do with that. So. Maybe I've just given up, but that's sort of where my thinking is these days.
So do you have comments on where we should be with
No,
generators in
no.
a couple of years?
I think I've already said.
Okay, then I don't know how far we can get, because as you have heard, we took almost 2 years to just implement an MEC and a spectral function in the Newt, and so it will take a long time to do new things. So we like to have the better implementation or the modification or the tuning. He doesn't like the tuning, but I say the tuning, because the simple implementation of the spectral function with the MEC doesn't agree with data or ours completely. So we have to think about what we can do further. So that is the next year, coming years, I think. Kind of study what we can, or what theories can improve, or what theories can say to us. That is the next thing we have to do. That's all.
Yeah, probably I don't have much to add, and I can say, well, I am in this environment about 10 years, so I must say that, I mean, for the first probably 8 years or so, I mean, there was not much progress and probably not much motivation to improve Monte Carlo. So for years and years, I mean, they were based on the same model, Rhein-Siegel, Fermi gas, and I mean that what I see that during last probably, I don't know, 2 years or so, there is a lot of activity. So there's a lot of work going on in Newt, probably also in Gini to improve. I understand that, I mean, there's a pressure from experiments, I mean, to improve predictions, to constrain the errors, and this is great. So it is very, I mean, where we will be in 2 years, I mean, depends, because, I mean, it does not make much time, take much time to add a new model, or to incorporate some new data. So I think it depends. I mean, as far as physics is concerned, I mean, it depends on developments, on critical developments, and on the maybe some measurements. I don't have anything specific in mind. So again, it is difficult to predict. And
I haven't heard much mention of LBNE in these discussions, right? So LBNE is something that's going to take a little bit longer than 2 years, but in 2 years, we're going to start thinking about how we achieve these fully relativistic goals that we're going to need
That's right.
for LB&E, right? So can that not be part of the planning that we actually begin now?
Maybe that's.
How precise you actually need for the planning of the experiment? That is not clear to me. I'm living in Japan, so I don't know the details there really inside. So
There is a lot of discussion on whether LB&E can actually be successful in the measurements they want to do at the 1% level, for example. Can we actually see a way of either negating that or substantiating that to help them or the community better understand what can LB&E actually do? That's a dangerous mission, no doubt about it, but it's something that I think the community would like to see.
One comment I can make is with my LB&E, even with my LB&E project hat, I can make this comment. And that is that actually, as part of the review process, certainly what's been done, what's been shown for LB&E sensitivities and the way that's been produced is not sufficient. In the next, basically, call it 3 to 4 years, LB&E needs to state in, again, not every nut and bolt and not every detail, but needs to have more of an oscillation analysis plan and have some level of evaluation of the uncertainties at each stage of that plan. Again, I mean, as everybody knows, nobody will really know how to do the analysis until the analysis is actually done and data are collected. But certainly there needs to be, some kind of baseline plan that addresses some of the fundamental issues.
Yeah.
This is critical, for example, to understand what the true requirements are on the near detector. I think in the past, most experiments have been focused on, what's the either what can we get away with at the near site, or what's the near detector we can afford, or what's the near detector that our country would like to build for this particular experiment, or something like that. And LB&E needs to, because it will need its near detector to make these measurements, will need to say, at least in I mean, again, not every little detail, but at some level, what measurements are going to be made and how are those going to be applied to the oscillation analysis. And we'll need to do this on a time scale of a few years in a general sense. So for LB&E, that's certainly quite critical.
This
This
gives an ideal hint for me here. Can I just turn that on again? Because my recent involvement was triggered by LB&E and by the LB&E proposal, which I thought was excellent, was interesting, but